Hello, in this video we're going to be graphing the parent functions of logarithms. We're going to start off with a simple logarithm. It's simple to get your head around, log base 2 of x. Y equals log base 2 of x. The thing is about logarithms, it's the inverse of the exponential function. So sometimes it's easier if we rewrite this. So it's a base 2, so it's 2 raised to the y power equals x. So when we go and do our table of values, x comma y, it may actually make more sense to start with the y values because people can kind of get their heads around powers of 2 to some power. But the table of values will be the same as we always will have. So why don't we start off with a pretty basic value, 1. 2 to the 1 is what? Well, 2 to the 1 is 2. So 2 comma 1 is a classic point for a log base 2 of x. How about raising something to the 0 power, 2 raised to the 0 power. Now remember your exponent rules. Anything raised to the 0 power is actually 1. And this is what I call a classic point or an anchor point. Because you're going to actually have the point 1 comma 0 in every parent logarithm. Doesn't matter what the base is. If it's just a basic log, you're going to have 1 comma 0 as an anchor point. How about raising 2 to some higher powers? So say 2 squared. Well, 2 squared is going to be 4. So log base 2 of 4, log base 2 of 4 is 2. And I think we can stop there. How about we go fractionally? Now, the thing is, if we were to plug in a value of x that is negative, well, negative logarithms are undefined. And we'll see why very quickly. Let's raise y to let's raise 2 to a different power. So we've got 2, 1, 0. Let's try negative 1. 2 raised to the negative 1 power. Now remember your exponent rules. When you raise something to a negative exponent, you take the reciprocal of the base. The reciprocal of 2 is 1/2. So 2 raised to the negative 1 power is in fact 1/2. So getting back to logarithms, log base 2 of 1/2 is negative 1. And let's go to negative 2. And again, you remember your exponent rules. 2 raised to the negative 2 power is going to be 1 over 2. That's the reciprocal of the base, but we're going to raise this to the second power, and that is 1/4. So if we have 2 raised to the negative 2, that's going to be 1/4. But again, in terms of logarithms, log base 2 of 1/4 is negative 2. Right? I think we have enough to start doing our graph. So I guess we can, well, let me start with our anchor point because I just really like this point. 1 comma 0. This point is going to be on every logarithmic graph. If it's a parent function, it doesn't matter what the base is. And going forward, 2 comma 1, this is another anchor point in that this 2 is actually the base. So log base 2 of x, you're always going to have this a situation where it's whatever the base is, comma 1. All right. In this case, it's log base 2. And what else do we have? 4 comma 2. So let's go over here to 4 comma 2. So we see we're curving to the right, curving not downward, but we're decreasing our slope. And now let's do x is 1/2, y is negative 1, and then x is 1/4. Y is negative 2. So I think you see this is going to be curving downwards very, very gently. So here's our graph. And I'm going to try to hit these points with a smooth curve if I can. Okay, and you put an arrowhead on. Now, what's happening as we get closer and closer to the y-axis? Well, we're going to have an asymptote as we get closer and closer to this y-axis. So let me just highlight that. You're going to have an asymptote right here. This represents the asymptote. Okay, A-S-Y. That looks horrible, doesn't it? So we're going to have an asymptote at x equals 1. A-S-Y-M-P-T-O-T-E. Should be on your spelling test. An asymptote is going to be at x equals 0. So our graph is going to get infinitely close. Now that we're talking about things like asymptotes, we might as well continue our discussion with domain and range. So our domain, our legal x values. Well, if you take a look at the legal x values, again, we cannot take a logarithm of a negative. We also cannot take a logarithm of 0. There is no value. If you look at this function right here, there's no value of y that's going to cause this expression to equal 0. So our domain is going to be x is greater than 0. X must be greater than 0. Not equal to, must be greater than 0. Now our range, if you take a look at the y values, or the thing about parent functions is you really can see the range of values. And I hope you could see from this table, we could have picked any value of y. We could have picked something close to positive infinity or something close to negative infinity. So the range is actually all real numbers. Now the way you write that with an inequality, we can go from negative infinity is less than y, which is less than positive infinity. Okay, that's the range. Now let's take a look at a standard log or a base 10 log. And we're really going to have the same situation. Let's do a table of values. Well, first off, let's rewrite this. Log of x really means log base 10 of x. We don't write the 10. So if we were to write this in exponential form, this would be 10 to the y equals x. And if we want to make a table of values, x and y. So before we kept cheating by plugging in here, but now let's actually just talk about actual logs. So for example, what is log of 10? Well, it's log base 10 of 10. So 10 to the what is 10. So if I plug in 10 for x, what am I going to get for y? I'm going to get 1. How about log of 1? This means 10 to the what is 1. Well, you should remember that anything to the 0 power is 1. So this is going to be 1, 0. How about something like log of 100? Log of 100, well again, 10 to the what is 100? That is 2. 10 squared is 100. And now we can't go in the negative direction for x, but we can go in the fractional direction. How about log of 1/10? Well, 10 to the what is 1/10? 10 to the what is 1/10? That would have to be a negative 1. And log of 1/100th is negative 2. So let's plot these on our graph. Now this graph is going to get kind of ridiculous. So we are counting the individual grid squares, and I've already labeled this graph for us. But let's actually take a look at these anchor points that I keep talking about. 1, 0, 1, 0, and I love this point. This is what I call my anchor point. It really doesn't matter what base we have. You're always going to be graphing 1, 0 if we're doing a parent function. Then we have 10, 1. Now, what did I say about 10, 1? This depends on your base. So 10, 1, this really depended on the base. This was log base 10, so that point is really dependent on our base. Now, if we go way, way to the right, we're going to get 100, 2. So this is a very, very shallow graph. And it's also going to get very, very steep in a hurry. So 1/10, negative 1, and then 1/100th, negative 2. So this gets ridiculously steep. Okay, I can't even draw it. And then it really is shallow. Okay, so that is our logarithmic, our standard log base 10, or just what we call it y equals log x. Now, what about our domain and range? Our domain and range, RNG, are the same as before. Take a look at the legal values of x. Oh, you know what I forgot to do? I forgot to put in our asymptote. See if I can pick a color that'll be visible. We're going to have an asymptote here. Okay? Our asymptote is actually going to be x equals 0 is our vertical asymptote. So how about our domain and range? Our domain, well, we can't have all values of x. We're limited as to only x is greater than 0. And our range is all real numbers. All right, you can have any value of y. Hope you see from this table, even though the x values get ridiculous, you could really put in any value, any negative value for y, any positive value, including 0. Now the last thing we're going to do very quickly is we're going to plot our natural log. Now a natural log is really nothing more complicated than a log base x. So this can be rewritten as y equals, I'm sorry, not log base x, log base e is what I was trying to say. This is log base e. Now what is e? That's Euler's number, and e is approximately 2.718. All right, it's Euler's number. So we're going to see with our table of values, in fact, we're going to actually make a table of values that is tailored to e. So starting with our favorite point, how about 1? Natural log of 1. Now again, natural log of 1 equals what? What does this mean? This means e raised to some power equals 1. Well, I hope you recognize that that has to be 0. Anything raised to the 0 power is 1. So that is our classic point, 1, 0. I keep calling this our anchor point, 1, 0. I don't know what other teachers call it. I call it an anchor point because it just keeps showing up no matter what log we have. We're going to have 1, 0 in the parent function. What happens if we have something like e for x, which is approximately 2.7? And again, e to the what equals e? Well, this would have to be 1. So it's e comma 1. So again, 2.7, approximately 2.7 comma 1. What happens if we go not in the negative direction with the x, because you can't go negative direction, but what about 1 over e? Okay, 1 over e. Well, this would have to be negative 1. Now, what's 1 over e? That's approximately 3.6. I'm sorry, 0.36. Approximately 0.36. All right, and how about e squared? Well, e squared, or the natural log of e squared would obviously be 2. All right. Now, what is e squared? That's approximately 7.4. E squared is approximately 7.4. So let's actually try to graph this. It's not the same number of points as before, but now we've already graphed 1, 0. Now let's go over to e. So this is 1, 2, 3. Well, we want 2.7, 1. Okay, this is e, 1. All right. How about e squared? Now e squared is 7.4 approximately. 1, 2, 3, 4, 5, 6, 7. 7.4 approximately, and then come up to 2. Okay? That's e squared, 2. Now on the negative side, or not the negative side, but on the fractional side, we have 1 over e. Now 1 over e is approximately 0.36. So that's a little bit bigger than a third. All right. So if we were to sketch a line between these points, you'd get something that looks approximately like this. And again, doesn't actually hit the axis. It gets infinitely close to the axis. So we can actually have our asymptote, okay, our vertical asymptote. Never actually hits. So let's talk about domain and range. What is our domain? And what is our range? Well, the domain, again, like before, x has to be greater than 0. The range, all real numbers. And that's it for parent functions of logarithms.